Hello everyone, myself Forum Mokwana, Assistant Professor of EC Department at LG Institute of Medical Technology. Welcome to the session of satellite communication. So in the last session we have finished chapter number 7, that is the Earth segment. So in today's session we are going to start from number 8, that is a satellite link design. So in this session we are going to cover saturation flux density. What do you mean by system noise temperature and G by T ratio? What is noise figure and noise temperature? And the G by T ratio for the Earth station. Now, saturation flux density means what? We can say that the power received at the Earth station from a satellite is basically the fundamental understanding of satellite communication. Okay, so we need to calculate the received power. So this received power will be dependent on the distance that it can travel from the transmitting station. First, then second, what is my transmitting source in the free space, which is going to radiate a total power of PT, that is a transmitted power, which is uniformly distributed in all directions. And that source is called the isotropic because it can transmit the signal equally, uniformly in all directions. Alright? So if you need to measure the received power at distance of r, then we need to calculate what do you mean by saturation flux density. So it is nothing but the received power at certain distance. Okay, so we can say that my distance is r meter from the isotropic source, it is from my transmitting antenna. So this flux density will be Pt divided by 4 pi r square. Its unit is watt per meter square because the power is measured in the watt and the distance is measured in the meter. Alright? This is the example how my power is going to be radiated and how it is going to be received. See, consider that circle, that is my isotropic power source. Okay? That is my effective isotropic radiated power, which is equals to Pt watts. And at certain distance of r meter, I will get a specific flux density, that is the F, saturation flux density, is called the watt per meter. So it is the flux density produced by the isotropic source. Alright? Now, if we need to calculate the power received by an ideal antenna with the area ampere per meter square, or you can say the area A having the value meter square. Okay? So this incident power density is equals to Pt upon 4 pi r square. So the received power is dependent on what is my saturation flux density multiplied by the area for the area on which the power is going to be received. Okay, so this is called the received power formula. Alright, so the power transmitted by the isotropic source at a certain distance of r, the signal is going to be received. Okay, and that signal is, after receiving, it's called saturation flux density, for which a particular area of my antenna. Okay, so for the transmitter with the output of Pt watts, which driving a lossless antenna, which is having a specific gain, you can say the GT. So if you need to calculate the power density distance, or is the flux density distance r meters, okay, this way. So the saturation flux density is equals to the PTGT upon 4 pi r square. We know the formula of saturation flux density, it is a PT upon 4 pi r square. Why we need to multiply GT? The reason is the transmitting antenna has a specific gain, so we need to multiply it, this function with the gain. Okay, gain is limitless That's why the unit of this saturation density, flux density distance R will be the same. Okay, watt per meter square. The product term, we can say a PP and GT, is called the effective isotopic radiated power. That is EIRP. Okay. What it defines? It defines the combination of what is my transmitting power and what is the antenna gain. Alright. In terms of isotropic source, that is PT into GT watts. Alright. So in such a case, if we consider the ideal receiving antenna with an aperture area of a meter square, we can collect the received power by multiplying the saturation flux density with the area of my antenna. Okay, aperture area of my antenna. Alright. So my received power is F into A watts, because meter square is going to be cancelled out. Right. So practical antenna with its physical aperture area of a meter square will not deliver the power in the harmonic equation. So what we need to do is, we need to consider its physical aperture and its effective aperture as well. Okay. So the effective aperture is going to be calculated by its aperture efficiency. Why? Because the sum of the energy which is going to be incident on the aperture, it will be reflected away from the antenna, and some is going to be absorbed by the lossy components. So we need to calculate the effective aperture. Alright, that is AE is equals to NA into AE. Alright, that is what is eta A? Eta is in the aperture efficiency of the antenna. So ideally, for parabolic reflector, its aperture efficiency is between 50 to 75%, and for the horn antenna, it is having the value of 90%. Alright. Now, the power received by the real antenna with the effective aperture area, that is AE into meter square. We can say that received power is equals to PT GT into A upon 4 pi R square. Alright. So the fundamental relation in the antenna theory is gain and the area of my antenna. If the area of my antenna is larger, then my antenna will receive the more power. Alright. We know the relationship between the effective aperture and the gain. So G is equals to 4 pi AE upon lambda square. Right. So we are going to substitute this above equation 4 pi AE upon lambda square into this equation. We will get PT GT GR upon 4 pi R and square and 4 pi R lambda whole square, that is the watts. So this expression is known as the Mill equation, which is essential in the calculation of received power with any kind of radio link. Alright. So this term 4 pi R upon lambda whole square is known as the path loss. Right. Now, by collecting the various factors, we can write the power received by antenna is the multiplication, or we can say the EIRP is going to multiply with the receiving antenna gain divided by path loss. Okay. So in decibel, we can say that what is EIRP? It is product of PT and GT. Alright, so PT, GT, GR by 4 pi R upon lambda whole square is in watts. Right? So EIRP, if you need to represent in the dB form, and if it is in the multiplication form, plus sign will be there, plus GR minus path loss. Alright? EIRP means 10 log base 10 PT into dB watt. GR means 10 log base 10 4 pi A upon lambda square. And the path loss means 10 log base 10 4 pi R upon lambda whole square in dB. Alright? Now, The equation B, this equation, represents in the ideal case where there are no additional losses in the name, only the free space losses there. Okay. In practice, we need to consider all the loss because we need to consider the more complex situation in which that loss is present in the atmosphere as well because of the attenuation by the different gases present in the atmosphere, like the oxygen, water vapor, content of water vapor, right? Rain, the losses in the antenna itself at each end of the link. Alright? So for that, we are going to consider the losses like first LA, the attenuation in the atmosphere. Second, the loss associated with the transmitting antenna itself. Third, the loss associated with the receiving antenna. Okay, these three are the losses we need to encounter while we need to consider the practical situation. Alright. So the received power PR is commonly referred to as a carrier power. Why? Because the most satellite link will use either frequency modulation for analog transmission and the phase modulation for the digital transmission. So both the modulation scheme, that is the amplitude of the carrier, is not going to change when the data are modulated onto the carrier. So my carrier power is equal to the received power. Alright? Now, the next topic is the system noise temperature and G/T ratio. What does it mean? First of all, at microwave frequency, a black body with a physical temperature, we can say it Tp, degrees Kelvin,